Hi, I hope that you all are doing well and are warm in your homes and cozy and not having to get out and drive in this stuff. So, today we are going to go through a little bit of chapter one. This is part of unit one. We will be covering in the second week of lecture some of chapter one, chapter two, and chapter three. So today, though, we're just going to be hitting up three sections in chapter one. So this first slide here is just a reminder of everything from what we talked about on Wednesday with the lecture part. So you're going to be using the online platform to access this content and some other content, and make sure that you read through your syllabus so that you know where everything is and how much everything counts towards your grade. I also have here again the Alex code. So this is for you to do your homework. You need to create an account in Alex, and this is also for you to access your online textbook. There will be a homework assignment this week that is based off of the things that we do in this lecture. So make sure that you go on to Alex, create your account, and then complete that homework. So we'll start out with section 1.2 of your textbook, which is scientific measurements. So, chemistry is one of the sciences that is very heavy in math and measuring. We're often taking lots of measurements in the lab, and most of the measurements that we take are called quantitative measurements because they are expressed using numbers. So every measurement provides three kinds of information, and these three pieces of information are very important that you record with your measurement. So the first one is, of course, a number, and this gives us the size or magnitude of the measurement. The second one is what's very important in science, and that is a unit, and this gives us a standard of comparison. So, like, meter, gram, kilogram, those are units of measurement, and it is very important to always include your unit of measurement. And then the last thing we're going to spend some time talking about is significant figures. This is an indication of the uncertainty of the measurement. So basically, what it tells you is how precise, or tells the other person that's looking at your measurements, how precise the measuring device was that you were using, because you cannot record a measurement that is more precise than your measuring device. So here we have an example of a measurement from a lab. So you see we have 45.2 centimeters. The 45.2 is your number, your size or your magnitude. The centimeters here is your unit. This is your standard of comparison. So you know that you can compare that to other centimeters or to how long an actual centimeter is. And then the last part is the fact that there are three numbers in this 45.2, and that represents three significant figures. And we'll talk more about significant figures and how to determine those later in this lecture. So one of the important things is to know your SI base units. And the SI system, or the International System of Units, is an updated version of the metric system. In science, we always record our measurements in the metric system. This is because there are only a few countries left in the whole world that still use the imperial system, and we are the largest of those countries. The other two are like Liberia and Myanmar, I believe. Um, so, since the majority of the world uses the metric system, and as scientists, we're expected to share our results with people, those people are not always in America. So, we use the metric system as our main unit of measurement in science. So you have seven base, what they consider base SI units, and then other units are often derived from these. So these seven units are length, mass, time, electric current, temperature, amount of substance, and luminous intensity. The ones that we use most in chemistry are length, mass, time, temperature, and amount of substance. Now, electric current you might use in Chem 2, but in Chem 1, these are the ones that we use the most. And amount of substance is an extremely important one for us that we will discuss a lot in the coming weeks and what you'll use throughout chemistry. Now, what I think is funny about the amount of substance, which is the mole, not the furry kind in your backyard, but the chemistry mole representing the amount of substance, is that most of our units are symbolized with one letter or two letters of a symbol just to shorten it for us. So I love that they way the shortened mole is MOL. So we take off one little bitty letter and that's the symbol for moles. I don't know why they just didn't leave the E on there, but that's just something I've always found humorous. So, one of the reasons that most people consider the metric system to be easier than our old-timey imperial system is that it uses prefixes. And this is the table of prefixes that you will find in your textbook. This does not include all of the prefixes that are out there, but these are the most common ones that are used in chemistry. And I would say that really here down are the more common ones. And that's because in chemistry, we're often dealing with small amounts. And so you will be using amounts that are smaller than the base unit more often than you will larger. And the one that you use if you're dealing with a larger amount is typically your kilo. But kilo, centi, milli, micro, nano, and pico are the main ones that you see a lot in chemistry. Now, you will be required to know these to be able to use them for conversion factors. And we'll talk about that a little bit further on when we're actually doing more mathematical problems. But it is going to be important for your first test and for a few of the tests later that you do know, for instance, that 100 centigrams would equal 1 gram. Or, for instance, 1,000 grams equals 1 kilogram. So things like that. And we'll work with that a lot more often. And you can see that these numbers here are represented mostly in scientific notation. But again, we'll go through those more as we are practicing problems. The first measuring amount that we talk about is mass. Mass we use pretty much all of the time in chemistry because we want to know how much of a substance we have. And mass is the measure of the amount of matter in an object or sample. It does not vary depending on your place in the universe like weight does. We often see that weight and mass are used interchangeably. And this is because obviously on Earth, they are affected by gravity. Well, I'm sorry, strike that. We use them interchangeably, but they are not the same. Mass is just the amount of matter, and it doesn't matter where you are in the universe. Weight is affected by the pull of gravity. And so when we're describing our mass and weight on Earth, we are describing our weight as being affected by gravity, whereas the mass is not. So our mass is going to be the same here on Earth as it is on Mars or Jupiter or anywhere else in the universe, whereas our weight would not be. So, although the SI unit for the mass is kilogram, we're often dealing with much smaller amounts than that. So, 1 gram is about the mass of one small paper clip. So, one small paper clip is about 1 gram. So if you think about a kilogram, that's going to be 1,000 paper clips. Well, we're not typically measuring something that heavy. So we use the gram, and all of our balances that we use in the lab measure with a gram. Now, one of the things that sometimes people don't realize or a common misconception is that some things don't have mass, but all matter has mass. We often think of gases, especially as being massless, but they are not. And you can see that in this picture here from your textbook. So, in part A here, we have a flask that is empty. It's called an evacuated vessel, it has nothing in it, and we see that its mass is 243.07 grams. Now here we have the exact same container, but we've added what looks like a yellow gas in here, maybe some chlorine or something. And so you can see here that even though it doesn't change a lot, it does change because adding that gas to that vessel increases its mass. So we went from 243.07 grams to 243.22 grams. And this shows us that all matter has mass. Temperature is another common measurement we're taking in the lab. There are two temperature scales that we use. Notice neither of those are Fahrenheit. In the lab, our thermometers will often read in Celsius. That's what they read in instead of Kelvin. But we know that Kelvin is our main SI unit for temperature. So this becomes especially important when you're learning more or taking measurements about gases. The unit for the Celsius scale is degrees Celsius, which is represented by our little degree sign here in Celsius. The unit for the Kelvin scale is just K or Kelvin. Notice it's not degrees Kelvin, it's just Kelvin. To convert a temperature from units of degrees Celsius to Kelvin, there is a very simple equation. All you would do is add 273.15 to whatever you have in Celsius. So, for instance, 0 degrees Celsius is equal to 273.15 Kelvin. A common measurement that we have is 20 degrees Celsius, or anywhere from 20 to 25 degrees Celsius are your typical room temperature. And if we add 273.15 to that, it's going to be 293.15 Kelvin. And we can easily do the conversion back to Celsius if we have a Kelvin temperature by just subtracting the 273.15. So it is a very easy conversion back and forth between Kelvin and Celsius. Another one that we use is length. And what I've included here is just a basic diagram that shows you kind of the comparison of some common imperial lengths that we know versus the metric lengths. So here you can see in this small ruler here that we see that 1 inch is equal to 2.54 centimeters. And most rulers or a lot of even measuring tapes will have both the metric system and the imperial system on them. So you can see that a centimeter is about 2 times smaller, 2.5 times smaller than an inch. Another common measurement are meters and in metric and yards in imperial, and you can see that they are very different. This is something that my high schoolers mix up all the time. I have meter sticks in my room, and they often ask for a yardstick, and I'm like, I don't have a yardstick, I only have meter sticks. And that's because if you compare the two, a yardstick is only 36 inches. Whereas a meter stick, if you were to measure it in the imperial system, is 39.36 inches. So there is a difference of a little bit over 3 inches. A meter stick is larger than a yard. All right, a lot of the units that we use in chemistry and measurements that we use in chemistry are derived units, and these are made by combining the base units. Some common examples that we often use are volume and density. So the SI unit for volume is the cubic meter. And this is something you should make sense to you because if you remember from school, from high school or elementary school, volume of a solid object equals length times width times height. Well, length can be measured in meters, width can be measured in meters, and height can be measured in meters. So meter times meter equals cubic meter. So that's where that unit comes from. Now, in chemistry, we're often dealing with much smaller amounts, and so we use the cubic centimeter. You notice here that I have a conversion factor that says 1 cubic centimeter is equal to 1 milliliter. Milliliter is our common unit for a liquid volume. That's commonly what we use because this would be something like if we were using a graduated cylinder, it's going to be in milliliters, recorded in milliliters. And then the cubic centimeter is often what we're using if we're talking about a solid volume, where we would be using something like a ruler that would measure in centimeters. So, but you can see that this is a 1-to-1 ratio, that 1 cubic centimeter is equal to 1 milliliter. Here we have density, which is another common measurement that we use to describe the property of a substance. And the equation for density is mass over volume. You can also use, if you might remember your high school science teacher showing you this is a density triangle. And in this, you have density, and then you have mass, and you have volume. I like to think DMV. So this helps you if you struggle a little bit with rearranging equations. You can use a density triangle as long as you remember DMV to help you figure out what your equation would be. So the way that you use this is you cover up whatever you're looking for. So let's say I'm looking for density. I would cover up the density and I'm left with mass over volume. So equals mass over volume. Well, let's say that I'm looking for volume. If I cover up the volume, then I'm left with mass over density. And then lastly, if I'm wanting to find the mass and I am given the density and volume, then I would cover up the mass and I'm left with mass equals density times volume. So it's just a quick way. You may not need it at all, but it's a quick way so that you don't get yourself confused on what goes where in your equation when you're doing these calculations. So the SI unit for density is kilograms per cubic meter, but that is often not the one that we use. Most often in the lab, we will use grams per cubic centimeter for solids, grams per milliliter for liquids, and then for gases, because they often take up a much larger volume, you see that we often use grams per liter. And here I have some common conversion factors for you. Grams per cubic centimeter is equal to 1 gram per milliliter, which is equal to 1,000 kilograms per cubic meter. Or if you're dealing with gases and you have 1 gram per liter, that is equal to 0.001 grams per milliliter. Let's do a couple of density calculations. If you want to pause the video here and try to work these out yourself, you can, and then come back and check your answers with me. Okay, so given that the density of methanol is 0.792 grams per milliliter, so we have density here. Calculate the mass of 25.0 milliliters of the liquid. So we're looking for the mass, and we have here the 25.0 milliliters, which is going to be our volume. So you can look at your density triangle that I have here, and in this case, we would cover up mass, and so we would be left with mass equals density times volume. So we have here our density is 0.792 grams per milliliter, and we are going to multiply that by 25 milliliters. If you put that in your calculator and do the calculation, then you should see that it equals 19.8 as our number. And then notice we're looking for mass. And in our problem, we had our mass unit was grams. So that will be our unit for our answer. We have 19.8 grams of the methanol that is used in this problem. Okay. Here we also have the density of water in our second problem as 20 degrees is 0.998 grams per milliliter. So this is our density. Now notice they gave us a temperature here, and we'll talk about the fact that density is affected by temperature later. But in our triangle or our density equation, we don't have a temperature. So that means that this is currently extraneous information for you, so you don't need that to set up this problem. We're looking for the volume here, and then they gave us the mass of the water. So we want to know that if the density of water is this at 20 degrees, if we have 4.50 grams, what will our volume be? So we look at our density triangle and we find that if we cover up volume, we are left with mass divided by density. So we just plug in our problem here. That would give us 4.50 grams over 0.998 grams per milliliter. If you type that into your calculator, you will get 4.51. Now, we look here, our volume amount that we used in here is going to be our milliliters, so we want to be consistent. So that is milliliters for our volume. Now, when we are calculating the density of a lot of materials, we are typically comparing those densities to the density of water at room temperature, which is around 1 gram per milliliter. So the water density, and it can change just a little bit depending on the temperature. As you can see here at 20 degrees Celsius, this is a more specific, but we can use our general knowledge that the density of water is around 1 gram per milliliter to determine what will happen with other things. So for instance, we look at our density here of our methanol, and you see that it's 0.792. Well, that is less than 1. So that should tell you that if I were to mix methanol and water together, that they would separate, and who would float on top? Would it be the water or would it be the methanol? Well, since methanol is less dense than water, then you would have water on the bottom with the methanol on top. So that kind of just that comparison gives us an idea when we're looking at different densities and how they compare to water. Now I'm going to stop the video here at the recording um, and split this up into each section. So once you finish this video and you're ready to move on to the next section, you can start the next video.